Thank you, Craig. And, this is always a hard time slot, so hopefully you all had some sunshine to keep you invigorated for the afternoon. So I'm just going to give a brief overview. My colleagues are going to talk a lot further about the results, but I just want to introduce you to the project and what we did rather briefly. So I first want to acknowledge my colleagues that are directly a part of the team that went out and collected the data. But of course, Craig wanted me to be sure to say that there is definitely the larger team of which many of you as end users have been an important part of and have guided this process all the way from the beginning. So we're very grateful for that. So let's see, I have to figure out how this works. Point to here. Okay. Well, you can't see the top of the slide, but what it says is our goals and objectives for this project were pretty simple, really. We wanted to determine what the end user needs were. So we held some workshops in the beginning. Dr. Bragg was very helpful in summarizing those end user needs. We also then our primary focus was to go out and collect an inventory of the carbon stocks in the as many wetlands of the Pacific Northwest that we could, and put those data into a database and populate that database with other data that was available throughout the region, and then share the results, which is what the purpose of this workshop is today. So, not sure how to do this. Is there a trick?
It keeps doing this for some reason. Just have to click on it.
Okay. So just by way of introduction to the kinds of areas that we were looking at, we had tried to cover basically the entire tidal range of Pacific Northwest coastal wetlands, and also the range from saline to tidal freshwater. So in the submerged aquatic, we really focused only on eelgrass in the submerged saline part. But in emergent wetlands, we had the full range from saline pickleweed marshes up through tidal freshwater, and in both low marshes and high marshes. We decided to not include the shrub-scrub community just because there are very few of them out there, and it was just going to spread our sampling a little bit too thin. So we included instead the Sitka spruce forested wetlands. So we had 34 sites in total, and I know you've seen this map now about 5 times already today, but if we keep showing it, you're going to have it committed to memory. But my point is really just to show that we distributed the sites throughout the study area, including Northern California, but also that we grouped the sites as much as we could within estuaries so that we had the full range of habitat types represented where we could. And at each one of those sites, we took as much information as we could, and that was partly why we focused on those particular estuaries, because they were places where we had some existing information. So we used elevation data, historical land cover data, to really help guide where we wanted to target the collection of our core samples. The far right side there just shows an example of how we distributed the cores within a site. We had a random start location and then at equal intervals 20 meters apart. So at each site, we collected 6 deep soil cores. By deep, I mean 1 to 3 meters. We went as deep as we were able to stab down with a avalanche probe. Yeah, we use an avalanche probe to determine the depth of the sediment and then cored down as deep as we could possibly go. We also collected 12 above ground biomass samples and then collected data along the transects at each site on downed wood, following Forest Service recommended methods for doing that. We identified all the trees and shrubs within diameter surrounding the plots and identified the dominant vegetation cover. So we also looked then, we surveyed the elevations at all the sites and collected information on some of the environmental drivers having to do with the hydrology and the salinity at all of the sites. So the distribution of the sites was not quite equal, but we did get a good representation of all of the different kinds of habitat types in addition to 6 pasture, diked areas for comparison. So I just want to introduce then my colleagues. Boone Kauffman is going to talk about the carbon stock results, and Chris Janousek will talk about the environmental drivers and some of the preliminary results we have from that and how it relates to the carbon stocks. And Chris will also give an overview of the database project and where that's at. So Boone is somehow going to join us.
So Boone Kauffman is in Corvallis. So we have the disembodied voice of Boone Kauffman from Corvallis.
Yes, hello everybody. It's so good to have this opportunity to visit with you all this morning. I'm real sorry I couldn't make it. I would love to blame Alaska Airlines who changed my flight from last night when I was hoping to get to Coos Bay to this morning. So I sad to say couldn't, and the best I can give you this remote presentation about blue carbon stocks. But anyway, hopefully everybody can hear me. If for some reason you can't, let me know, because all I'm doing is talking to a screen. And the only weird thing about this is I'm in my underwear. Not really. Don't want to paint a bad picture. But I am just sitting on my kitchen table doing a presentation, which is always kind of weird. But anyway, I'm going to talk about blue carbon stocks and the results of our research that Amy so eloquently described earlier. And similar to what, in addition to this wonderful blue carbon team been working, I also want to acknowledge many of the co-authors that came from OSU, particularly Lila Giovanoni, one of my graduate students, who was one of the field leaders throughout this project, and also some of the best undergraduates, future blue carbon leaders and wetland scientists.
Guest speaker.
Anyway, Jim Kelly and Nick Dunstan, 2 undergraduates who were as well as Ian and Al folks, and Amy and Craig, all together, again, in terms of the education, not only are we generating a great deal of science, we've provided an educational opportunity, research opportunity for 10 undergraduates, research, and of which at least 2 undergrad, probably 3 undergraduate honors college thesis, and engineering required theses. Logical engineering is coming. Similar to what is said, I'm going to report on the areas that we've sampled from the Humboldt-Eschler up to Padilla Bay. And again, I just want to acknowledge that none of this work would have been possible without the collaboration and advice and cooperation of all of the project team listed here. So, one of the things I just wanted to say is, not to be bragging, but last week I was sampling blue ecosystems, or actually I was given a blue carbon ecosystem in this ecosystem in Baja California, and it's just a remarkable, it shows you the breadth that we have of these blue carbon ecosystems throughout the world. You can see the small, low, red mangrove in the background with the cardon cactus and this Baja California, this incredible dry southern extreme of the Sonoran Desert is the uplands. And that same species is the same tree that you see on the right from the Amazon basin. So tremendous plasticity, ecosystem of the world. One of the points I just make is that this is not only a really important regional study, but I think they're pretty important global contribution to blue carbon. It's in that terrestrial system really is remarkably lacking in our quantification of rocks, particularly salt marshes. And again, this has led to us a lot to this. If you can just look at the study by you see on how much estimates of carbon storage as of about 2011, 2012 have been made, probably nothing in the Northwest at this point in time, certainly motivating us and begin to contribute to the database of blue carbon in these ecosystems. And of course, it also underscores the importance of just how much lost in the North. And California, of course, losing 91% of its wetlands. Oregon, they clearly much higher. Coastal wetlands, for example, are tidal swamp forests. Perhaps as much as 88% of them have been lost due to
Lost your Boone.
well, there.
Yeah, we're here, but
Oh,
we lost the share. The shared screen is gone.
okay. Second, somehow I keep on zooming in and out. See. Back?
Yes.
Okay, sorry about that. I don't know why. We're probably, I apologize for that. So our research outline is as the global research objectives, just to reiterate, we want to know what are the existing ecosystem carbon stocks to dominant wetlands in the Northwest. And coupled with that, of course, was to develop methods that could repeated and simplified methods that end user groups can use in the future, so that at some point in time, when blue carbon ecosystems become part of regional, state, national inventories, they could be easily included, incorporated, established in the Pacific Northwest. Once we get an idea of stocks of the intact ecosystems, we want to know how does land use, the conversion of the swamp forest to, say, cattle pack, how does carbon stock or potential emissions from that, and we're using an IPCC stock change approach, and then again looking at relationships of carbon stocks to environmental variables, and can we develop cost-effective approaches to quantify carbon stocks earlier for climate mitigation, adaptation approaches. Similar to what Amy showed earlier, we sampled along the gradient, the tidal flat would be the eelgrass communities. We sampled marsh communities, high marsh communities, and the communities might be where the citrus spruce marshes would be in this simplified diagram. Roughly show some of the sites we sampled, some of our studies. You can see our Transect Bay, Glacier Earth Reserve. Here's our South Slough sites. Again, our low marshes, we had this variability in composition amongst these sites. Some sites, such as this, the low marsh, of course, in South Lewis, Sarconia, we have dominated by Disticlus, as well as in this site, in Washington, that was a Juncus dominated low marsh site. High marsh, similar variation in composition depending on where we're at. Scarabslindia, Discantia, Chinoplectus, and Skagit, and variation not only noted in vegetation, but the texture, as well as horizon. And then, of course, the tidal forests we sampled, they're largely Sitka spruce dominant, but also it's important to note that we had approximately 18 different woody plant species of which we had to find equations in order to get the above ground biomass estimation. So tremendous diversity of vegetation of plant species growing in these tidal forests as well. And again, just another view of the Chehalis floodplain site that from across the channel. Just real quickly, here's just the numbers that we sampled: 6 eelgrass, 8 low marsh, 8 high marsh, 6 tidal swamp, 6 pastures. The range in pore water salinity. This is the salinity that was water in the soil, so the surface at time of sampling. So this would be during the summer months. And you would expect, basically a little bit higher in the low marshes, high marshes, the tidal swamps being, of course, the lowest in salinity. And again, we see pHs. A lot of times we measure pH just to give us an idea of whether we need to do any sort of adjustment for soil carbonates. These were usually slightly on the acidic side. We did find that we had very, very low carbonate or inorganic carbon in these soils. Our soil depths, and it was very important for us to sample our carbon top of the entire soil horizon, measuring, as Andy said, with an avalanche probe to get to the point of refusal or bedrock or indurated horizon. And these would range anywhere from eelgrass from 111 centimeters to 3 meters, which was our default depth. And then above ground biomass here is just how much, what is the biomass, not carbon, but total biomass of the sites. Our methodology, this is an approach. We've sort of used very similar approaches that we throughout blue carbon ecosystems, marsh communities, other eelgrass communities, mangroves. And we adapted that for the marshes in the Pacific Northwest for the Sitka spruce forest. Basically it entails a transect that's 100 to 125 meters long. Every 20 meters we're sampling the ecosystem stock at that site. So the data that I'll present to you today is actually the mean ecosystem carbon stock of 6 sites at each of these areas. So at each of these sites, we're measuring, basically following intergovernmental climate change protocol, above ground biomass, below ground plant biomass, wood where it's appropriate, oils, and other vegetables, trees and other vegetation besides trees. You can see that in the swamp, we use a 10-meter radius plot, measure all the large trees in that 10-meter radius. Trees less than 5 centimeters are in a nested 2-meter plot. Barkwood is sampled with the planar intersect technique, 4 transects per site. Mass is sampled in 50 centimeter plots, 2 in each of these sites, and then we extracted months before for the horizon, or 3 meters at each of the 6 sites. So again, the means that we report to of soils is the mean of 6 cores per site in these areas. So this is a pretty intensive carbon stock measurement relative to many other studies that you see in the literature. Our soil depth, is where we put a tremendous amount of effort given the overwhelming majority of carbon in these blue ecosystems stored in soils, and we partitioned the depth, the whole sort of horizon depth into these depth intervals of 0 to 15, 15 to 30, 30 to 50, 50 to 100, and then greater than 100 as deep as 300 centimeters if the soil horizon is deeper than or beyond 300 centimeters. And here's just example of the soil modified soil object that we do to sample the soils. It's very efficient at extracting a relatively undisturbed sample of the ground. And again, it works in virtually all of our sites, with the exception of pastures, which can be frequently compacted by years of livestock use. middle depth range, we'd extract heights per meter, or this core allows us to extract a site of known volume. We take that in, we try it in the laboratory, density. We also have got, from that, for that same sample, we get organic carbon, and we have also an organic matter as to come up, there are who use just organic, a very simple approach as a surrogate for soil carbon, to get an idea of the relationship there for future. And we've also looked at soil texture and this in these samples as well. Just to give you an idea, here's just the sampling approach. You can see the avalanche probe on the left while the crew is in soil auger, and then you can see soil probe in the woman's hand to the right at 3 meter depth. So we usually use a soil core site at the area where we got our depth measurement. And the analysis, again, like I mentioned, we're measuring both density, organic matter content, inorganic carbon. We just had to test to make sure we have very little inorganic carbon in all of our Pacific Northwest samples. Organic matter, using both loss on ignition as well as hydrogen peroxide digest. And from that, we've also measured soil texture on all these areas, as well as the entire horizon depth. Again, for the above ground biomass in the pastures as well as the marshes and seagrass, just clipped all of the above ground biomass in these 25 centimeter square plots. Just to look real quickly, like I mentioned earlier, we had pretty significant, when you're sampling between Humboldt Bay and the Canadian border, you get a pretty broad diversity of composition existing in marshes. This is a dimensional scaling exercise we did of just the composition. In each of the plots, not only we also of all of the species in the plot, and this is just basically the gradients of this multivariate approach based upon composition. And it kind of gives you an idea of along salinity gradients, which tends to be inversely related to the soil bulk density. But you see this beautiful gradient of species coming in and coming out as salinity, say, increases. You can see the process never on the top, highest and the lower salinity. There's salinity just a little, peeking out just a little bit more saline. As you move across into higher salinity, you see the light blue is the Janousek, Carnosa, and then you see, of course, the Sarcopenia and the Distichula spicata just continually increasing as salinity increases. So, we do find sampling some of these physical variables with composition, really interesting and differences in composition. That is largely you would expect. Okay, if we just look at total ecosystem carbon stocks, this is just a real quick look at the total ecosystem carbon stocks of every one of our 34 sites. And you can see the first thing you'll see is tremendous variability in the total ecosystem carbon stocks, as low as 75, 50 at Villa Bay, upper eelgrass, to as high as almost 1,200 tons of carbon per hectare in the Blind Slough Swamp. And as you can see, it's the darker green are the citrus spruce sites, the blues are high marsh, the light greens are low marsh, and then the olive greens are the Humboldt eel. And so you kind of see the species composite, or the vegetation type correlating well with the along this gradient of increasing carbon stocks. Those horizontal lines incidentally are significant differences with multiple comparison tests on the site basis at a p-value of 0.05. But anyway, I'll get back to statistics in a second. Basically, let me show you the data in another way where I separate them out now. You can see the swamp data on the left, the 6 sites of swamp data in the mean tidal swamp, and then you'll see next is the low marshes, followed by the third cluster is the high marshes, And finally, the eelgrass, obviously lower on the far right. We see the swamp. You know, one it did surprise us, low rates of ranges in total ecosystem carbon stocks. The swamp's 925 to 1100. Pretty high variation in the high marshes, 359 to 742. Pretty even higher variation in low marshes from 154 to 627. And then the eelgrass, the highest actual absolute variability from 68 to 389 tons per hectare. Real quickly, if I just look at the data now, just kind of like synthesizing it down a little bit further, these are the means of the eelgrass, the low marsh, the high marsh, and the swamp. Please excuse the comments. Okay, am I still there?
You're still
Okay,
there.
I'm sorry, my computer's going nuts. Any rate, am I still connected in, everybody? I still am. Okay. Anyway, this is the ecosystem carbon stocks based upon the average of eelgrass, the low marsh, the high marsh, the swamp. One of the cleanest data sets of any data sets that I've ever sampled in my career, in that there's significant differences at a p-value of 0.01 between each of these vegetation types. Of course, with the swamp being averaging over 1,000 tons per hectare, the next highest being the tall marsh, followed by the low marsh, followed by the eelgrass community. Wait just a second. Okay. If we just look at the eelgrass communities individually, again, here's we see the lower eelgrass again at Padilla Bay, a little bit lower than about 50 tons per hectare to as high in the Humboldt eelgrass as almost 400 tons per hectare. And what we're seeing here then is that Sally's Bend and Yaquina Bay and the Humboldt eelgrass sites, these were pretty fine textured soils. You know, these were largely, I think, like riverine deposited sediments, whereas lots of the other areas were more coarse textured soils, marine sediments largely. And I think this had the strongest impacts. Our hypothesis certainly this would get more analysis, giving it higher carbon stocks. Moving on to low and high marshes, you know, very similar types in the low marsh. You can see on the left low at Delta Island, Secret River marshes being less than 200 tons per hectare, getting up to 100 tons per hectare. The White River Marsh, the mean of 400. High marshes, again, significantly higher ecosystem carbon stocks in the high, ranging anywhere from about 300 in the marsh to as high as over 700 in Bell Marsh and Como Marsh, Danger Point. High marshes, South Slough, were very, very long carbon stock. These ecosystem stocks of the high marshes at the South Slough are some of the highest ecosystem carbon stocks of salt marshes measured anywhere in the world. And just an example, just some of the comparisons of similar approaches. These are data from a Mexican, a Syrian, the Yucatan, Australian marshes from the mouth of the Amazon, the IPCC default values of 4, which is about 225, I believe, and you can see our mean for the low marshes was a little over 400 and about 550 again for the high marshes. You can see, by and large, are a little bit at the high end of ecosystem carbon stocks for our marshes here in the Pacific Northwest. And then this is were measured by our research team. So the Mexican marsh, the Brazilian marsh, PNW high marshes were all measured using almost identical methods, certainly the same equipment. And these are just pictures of these marshes in Mexico. What's quite remarkable too is the low marshes in the Amazon are dominated by deciduous, and the high marshes were dominated by shiny wetlands. Incredible how we have the same species, the same general, and even the same species at these marshes measured at 0 degree, about 30 miles south of the equator. If we move on then to the tidal swamp, let's first look at just ecosystem. And so what you can see here is they can range in 70 hectares outer island to as high as 100 carbon per hectare at the Secret River Swamp. One of the things you can see is the Secret River Swamp, the Chehalis Surge Plain, and the Blind River Slough Swamps, the three largest swamps, were sites where we could really see very little exposed logging. Whole Johns River Island had been for a long time. In fact, that Johns River Swamp, there was stumps that were 3 meters in diameter and just amazing large trees that were once at that site. But what you also know, as well as this is the above biomass, the green is the trees. Look at the proportion of the ground biomass that's also the gold and the red is the downed large wood, and then the herb mass and the black is the tree root carbon. But you do see there's besides the trees, there's large wood that comprises a significant portion of ground carbon stock, especially in the old growth. It's the Blind, the Chehalis River, in the second growth sites that have been stored. But now if we just look at the total ecosystem carbon stocks of the tidal forest, is
Okay, great. All right, so I'm going to build off the results that Boone showed. We wanted to not only measure stocks in these environments, but really see if we could locate some environmental drivers that were correlated with stocks, and that would give us some predictive ability in terms of understanding carbon stocks throughout other estuaries in the Northwest that we don't necessarily have data for. So the main research questions relative to the environmental drivers piece are: how are stocks related to major environmental drivers such as inundation, salinity, elevation, or perhaps even climate variables across the region? We added another component. We hadn't planned on this in the proposal, but I've been interested in decomposition rates for a number of years, and we realized this was a great opportunity to get some decomposition measurements in association with our environmental drivers and the carbon data. So we added some litter bags to a number of our sites to assess that. So we wanted to know if those decomposition rates were correlated with the drivers and with sediment stocks. And then the kind of overriding question, and it's a theme obviously of the entire workshop, is how are these relationships useful in terms of informing wetland restoration and conservation and so forth. So this is a very rough conceptual diagram of the factors that might affect the carbon stocks in a given wetland ecosystem. So stocks are a function of plant productivity that adds carbon. Decomposition removes carbon from the system. Export removes it as well, and then you can have allochthonous inputs. And each of these 4 major processes in tidal wetlands are going to be affected by a number of drivers, and those also are interrelated. So things like salinity, inundation, geomorphic setting, grain size, and so forth. These all interact to affect carbon stocks. We looked at a subset of these, and not all of them, but we're able to sort of make some preliminary progress in understanding these relationships. So we had a couple of working hypotheses for this part of the study. The first was that carbon stocks in wetlands would increase with precipitation, and they would decrease with temperature. And this would be because of the varying effects that they have on plant productivity as well as organic matter decomposition. Another working hypothesis was that carbon stocks are higher in less saline wetlands. And related to that, carbon stocks are greater where there's increased soil saturation, so you have a higher groundwater table and more anoxic environment and less potential for decomposition, so you get a buildup of carbon in the soil. And then finally, we tested the hypothesis that carbon stocks were positively related to elevation within the intertidal. So these are our research sites, different maps, same sites, 34 distributed from Northern California to Northern Washington. And we sampled these 5 major habitat types. These are the sources of the data we use to test these hypotheses. So for our climate variables, hypothesis 1, we obtained annual mean precipitation data and temperature data from the Oregon State University PRISM model. So this is a model that covers the entire United States and gives us 30-year climate normals for any parcel of interest. We use the NREL irradiance model to get annual mean irradiance. So this is just how much sunlight is reaching a given site, and that in theory would be correlated with the productivity potential of the plants at that location. For our second hypothesis, we tested with our own field data. So we went out and deployed field loggers in channels as well as groundwater wells to get 1 to 1.5 year time series of water level and salinity in these wetlands. We measured decomposition rates using litter bags over a course of a half year in a subset of our sites. And then we use RTK GPS or leveling to assess the tidal elevation of all of the cores that we collected. And we used the VData model to estimate local tide range because that varies along the Pacific coast. Okay, so the first section are on the larger scale climate drivers. So what's happening across the region, and is there any relationship with carbon stocks? So again, we use the OSU PRISM model at a 800 meter resolution and the irradiance model at a 10 kilometer resolution to extract data from rasters. The climate normals are a 30-year average recent, and the irradiance are about a 10-year time series that have been averaged. Just extracted the values using GIS from our sites. And the data I'll show are just on the marshes and the tidal swamps because they're sort of the most similar habitat types across our study. This is the range in annual precipitation across the Pacific Northwest. So Humboldt Bay here on the left all the way to the Salish Sea on the right. And there actually was a lot more variability in precipitation than I expected across the region. It's all very wet, especially relative to Central and Southern California, but there are certain regions such as the Northern Oregon coast, Tillamook County area that are really particularly wet in the region. These are the relationships between precipitation and some of the metrics of soil carbon. So we looked at carbon content, just the percentage of carbon in the soil, the carbon density, so grams per cubic meter, carbon and nitrogen ratios, and then carbon stocks. I think the carbon stocks value there is for the top meter, it's for the top 15 centimeters only, but we could do that for all the different strata that Boone sampled. And really didn't see any strong relationships when we sort of pooled all of these habitat types together, low marsh, high marsh, and tidal swamps. There really weren't any strong relationships that jumped out. The next thing we looked at was air temperatures. So again, we have a gradient across the Northwest. It gets cooler as you go north in the winter, and it gets warmer as you go north in the summer. So we have this greater range in air temperatures across the region. But again, when we looked at the different carbon metrics in the sediment, really not even any weak relationships that fell out. So this was interesting, something that we'd like to test more with a larger data set. And then finally, at sort of the regional level, we looked at change in irradiance. Not much change, so the amount of incident solar irradiation is about the same no matter where you are in the Northwest. And again, no strong relationships with carbon variables. So one of the things that we can continue to look at is whether climate conditions affect the maximum stocks in an ecosystem. So they may not be very related to the mean values, but sometimes environmental factors can place a limit on processes such as productivity or decomposition, and then you can actually see relationships with maximum or minimum values. So we can take a look at that a little bit more. And then I'm going to be giving the next talk after the break on the database. And the database, as I'll show a little bit later, we have a much larger data set, and we have a broader range of environmental conditions because we're including some sites further south into California and farther north into British Columbia. So that may be actually a more appropriate data set to look at some potential climate relationships with carbon stocks. So the next hypothesis was to look at potential site level drivers such as salinity and inundation and decomposition. So to measure groundwater salinity, we deployed Odyssey connectivity loggers in groundwater wells and obtained time series of at least a year. We put these groundwater wells in the high marsh, tidal swamps, and a couple of the pastures. We did not measure eelgrass or low marsh where previous data, particularly from Laura Brophy, suggests that the groundwater in a low marsh is almost always near the surface, so not necessarily a lot of variation in those ecosystems. We've collected the time series, and we're continuing to process the data, so I only have a subset of data to show you today. In the same groundwater wells, we also deployed pressure sensors to measure changes in groundwater level. That was compensated with barometric pressure, as is often done in tidal wetland systems. And some of the metrics we can use to look at the groundwater data are the groundwater amplitude, so that daily or even seasonally, that variation in groundwater change, and then just sort of the average time that the root zone is inundated by groundwater. So again, we've collected the data, we've partially processed the data, but anyone who's worked with these loggers know that you get hundreds of thousands of data points, and it takes a long time to clean up and process. So for decomposition, we measured organic matter decay rates using the teabag method. So a number of you are probably aware of this. This is a standard method that was developed about over the last 8 to 10 years, and it uses two types of tea placed in litter bags. And the advantage of that is that the initial publications on this method have sort of worked out the composition of the tea and the expected decay rates and so forth. So we use these tea bags, we put them in a little bit sturdier material and buried them in the ground for about 6 months, weighed them beforehand, washed and weighed them again, dried and weighed them again afterwards. And we were able to put out replicate litter bags, I think 8 per site at 16 of our sites, so some of the high marshes, swamps, and pastures. And the two metrics that come out of the teabag method are a loss rate, so just a coefficient of decay with time, and then something that the original authors call a stabilization factor. And this graph sort of illustrates those two. So the rooibos tea, and these data, by the way, these are data on real wetland plants from California, but they kind of illustrate the rate of decay over a couple of years. So you get usually a relatively rapid initial loss of organic matter with decay. And the rooibos tea gives you a good estimate of that sort of initial rate of decay. And then eventually, if you wait long enough, and in this case 3 years is not long enough, we need to keep, they haven't quite leveled out, but eventually this curve would level out and it would sort of be reflective of your refractory carbon, how much carbon is sort of inert to decomposition and is going to persist in the site. And that's what the green tea estimates. So the green tea estimates sort of where things level off. The green tea decomposes really, really quickly within a matter of 1 to 2 months. So the first figures I'll show you here are the differences in the decomposition rate K and the stabilization factor S, which you get from the green tea, among our habitat types. And so in both cases, we found significant differences between high marshes, pastures, and tidal swamps. So pastures, interestingly enough, had the highest decay rates, higher than high marsh, but they also had the highest stabilization factor. So the organic matter that was there in the pastures is decaying very rapidly, but the characteristics of those sediments are actually preserving a higher fraction over the long term. And I guess I would probably treat these data as quite preliminary, given that we were not able to, our sample sizes were sort of relatively small, but these are some interesting preliminary results. When we tried to relate the decomposition rates to some of the carbon metrics, however, again, was sort of similar to the climate variables. We did not see really any strong relationships when we pooled the habitats together. And there may be sort of biogeochemical differences, elevation differences, salinity differences among these habitats that would suggest you shouldn't pool them together, but we don't have large enough sample sizes to kind of look at each habitat type independently. Here are some of the salinity data. Again, we're processing it, but made some progress on this, and I'm just showing you salinity data from some of the tidal swamp sites. So these are 5 of the 6 swamp sites. The 2 on the Columbia River are very, very fresh. So this is a 3-month period in the summer and or late spring and into the summer. And a number of our other sites, such as Otter Island and Snohomish and the Coal Creek Swamp in Halem, these are sites that do get more saline as the dry season progresses. So we had some salinity differences. And at least on a site level, these are summaries of the 6 cores that Boone took and the stocks to 1 meter depth. And you can see some trend in higher stocks at lower salinity sites. So the 2 Columbia River sites did look like they had somewhat higher stocks than the more saline sites such as Otter Island. And we'll be looking at that in the next 2 months as the project wraps up. We'll be completing those analyses for all of the marshes as well, where we also had the groundwater wells. So last thing I want to talk about is the within site elevation gradients that we had at each of our locations. So to measure elevation, we used RTK GPS. So this gives us an elevation with errors in the range of anywhere from 2 to 5 centimeters in the vertical. And then in some cases, particularly where there was very high tree cover, we used leveling. So we had a known elevation point, maybe measured with RTK GPS, and then leveled to that. The data that you get out of RTK GPS is a geodetic elevation, so it's sort of meaningless in a tidal system because plants care about inundation, not geodetic elevation. So to make it meaningful from the ecosystem perspective, we scaled all the geodetic elevation to a tide range elevation that we call Z-star. We measured, I'll show more on that in a second. We measured elevation everywhere in the eelgrass, marshes, swamps, and in the pastures. So to standardize elevation, we use this Z-star metric. Here's the equation for it. So it's your local geodetic elevation scaled to your tide range. So your mean high water minus your mean tide level. And the reason one would want to do that is that this Z-star is much better correlated with inundation than a simple geodetic elevation. And we have a really broad range of tide ranges within the Northeast Pacific. So as you move from California, this is the Northwest in this box, and then into Alaska, you get much greater tide ranges. And then even within an estuary like the Coos estuary, depending on where you are, you get differences in tide range as well. Okay, so these are some data that show the elevation differences among our eelgrass sites. So these are the 6 eelgrass sites that were studied. Mean tide level here at 0. A Z-star of -1 is mean local mean lower low water. And we had some variability. So these are sort of at the very bottom of the intertidal for the most part. The Volino Island seagrass meadow is a little bit higher. And these are the elevations of the tidal swamps. So again, this is mean tide level, flooded about half the time. Mean high water, flooded maybe 8 to 12% of the time. And the majority of the tidal swamp sites were slightly above mean high water. The Otter Island one was a little bit lower down. And then these are the elevations for the marshes. So we plan to sample both low and high marsh. I think what we found is that you can do one thing on the computer and then you go to the field and actually measure what you measured. And we found that we had really kind of a range of elevations across our marshes. So this one surprised me in particular. The Secret River low marsh site is actually below mean tide level, so it's flooded a lot. And if you recall from Boone's presentation, the carbon stocks were actually quite low at that particular marsh, so we probably have a big effective elevation there. But a lot of range, some like I think it's the Johns River one was actually our highest site of all in the tide range. So these are the relationships between the standardized marsh elevation Z-star and some of the metrics of carbon in the sediments. So on the left is carbon content with our tidal elevation. The dashed line is 1, so this is mean high water. Most of our sites were actually below mean high water. And there's a lot of scatter in that relationship, but a fairly decent relationship between elevation and carbon content. And then on the right side is carbon density. So this is grams per cubic meter. A little bit weaker relationship, but a significant relationship there. So the stocks really are higher in these high tidal wetlands. And that sort of has some gives us some impetus for conserving those areas, right? These are areas that have high carbon stocks. To lose them would result in significantly high emissions. So these may be some areas we want to target for conservation. Okay, and a couple more of the carbon metrics with elevation. The relationships do get a little bit weaker. So this is carbon stocks in the top foot of the soil, and then carbon stocks in the top meter. And these are these are marshes only. Sorry, I didn't state that earlier. Okay, and these are elevation relationships for the tidal swamps. So in contrast to the marshes, much more of a scatter here, really no significant relationship. The elevation range is much more constrained within the tidal swamps. They really can't grow far down into the intertidal, or at least at our sites, they weren't far into the intertidal. And then lastly, these are the relationships between the seagrass elevation and the carbon metrics. And again, not really a significant relationship here. Most of these seagrass meadows are quite low in the tide frame, so they're just getting inundated quite a bit. And there are probably other factors like grain size that Boone talked about that are probably more important drivers for the seagrass meadows. Yeah, sorry.
Chris, on the previous slide, we had some 1.075 carbon density values in there. Who are those guys?
On the right side?
Yeah, you got some really high carbon densities in there. What
Those right there. I'm guessing they are one of the Secret River, but that's just a guess. Because that Secret River site had really high soil carbon stocks. Yeah. Do those look anomalously high to you?
Yeah, it's good. Well, yes, they're very high. Because when we look at the national data sets, we tend to find 0.025, maybe 0.04 at the high end. And then the ones where we found values higher than that, it seemed to be that there was issues with the bulk density measurements.
Okay.
And so, maybe the numbers are correct, but it's always curious when you see numbers as high as that, because that means it's a really high amount of carbon per unit volume, so
Yeah.
it draws the attention as to what's going on.
Yeah, right, so that would be a good question for Boone since he ran those, but I'm going to punt on that one. But thanks.
Oh, I was just going to quickly say that I've seen numbers that high.
Yeah, I'm trying to remember these.
So,
I should have put on this
Although they
slide,
are-
but These may just be the top 30 centimeters, which are going typically have more carbon, lower bulk density, more carbon than if you're a meter down. I think these are the top 30. I should have put it on this.
You know what, using, for instance, San Francisco estuary as an example, high carbon content in the Sac Delta, low mineral soils, and higher density soils in the salt marshes for lower carbon content. But when you work out carbon density, it's the same number, 0.027 across the entire system. And so, your more organic systems are going to be more fluffy, and so you get a lot lower density. And so you have some numbers here, actually quite a lot of numbers, which are high carbon content, high density. So, yeah, it's interesting to explore what's actually going on in the field to get those kind of numbers, because they're higher than the national average.
Okay, yeah, no, that's good to know. I'm just going to go back to the marsh one here. So, yeah, they're quite a bit lower in the, no, actually, no, they do get up to 0.1, a handful of the marsh samples too. So I don't know if there's something unusual about a couple of samples that were collected. Okay. Yeah, thanks. Okay, so just to summarize those slides, in the marshes, we do tend to see a significant positive relationship between tidal elevation and carbon metrics like stocks. And then in the seagrass meadows, in the low intertidal, and the tidal swamps, we really didn't see a relationship with elevation. If we had we didn't sample any subtidal eelgrass meadows in this study, but if we had, we may see some relationships between depth and carbon content. Okay, so just sort of overall take-home messages for the environmental drivers. Climate, I was a little disappointed, didn't seem to really be all that important, but we've kind of talked in other workshops about why that might be, and this is something we could look at a little bit in a little bit more detail with a larger data set. Site level variation in salinity could be an important driver. It looks like it's a driver in the tidal swamps, and we're going to finish looking at that for the marshes. Elevation did seem to be relatively important in predicting carbon stocks, and again, that has I can't say that word today. That has impacts on where you site restoration projects and where you may want to prioritize conservation and management of tidal wetlands. Okay, so we're going to complete the groundwater work with those really large time series data sets, and then look at climate drivers with the database. That will be the next talk, but I think we're going to take a break, and I just want to thank everyone, particularly Craig, who did a ton of the field work to make this happen. So if you have any questions, otherwise I think we're going to do a break. Or any questions online?
No questions? Oh.
Just a quick question. The sites you selected are least disturbed or reference marshes?
Yeah, they're all reference. Yeah, except for the pastures, of course, but yeah, everything else.
Thanks.
All right, 15-minute break. We'll be back at